So this thing that you're seeing, AL, is basically G minus 2. So we are not interested in this 2 because it's trivial. So we subtract the 2 and whatever left is we call the anomaly. The anomalous magnetic moment. Okay? So this thing, if you write down, so it will have a part that is coming from everything that we know. For example, the electromagnetic interactions like coming from the photons and electrons and these things. Then another part will be hadronic, which means quarks and gluons inside this block. Then there will be weak, like W bosons and Z bosons and these things, okay? So all these things in this green part means everything we know. We calculate all these things. Then there can be a part that we don't know, okay? So to know what is the amount, what is the contribution from this part, we need to know very well this part. We need to calculate this accurately. Okay? So, now I will talk about how this, for example, this part is new, but this part is no. But anyway, whatever is inside this block, how do they contribute? How do they look like? Okay? Suppose you calculate a diagram with some particle flowing in the block. Here, for example. Or here. If we know it's a photon, right? It can be anything, something else. So, inside this block, suppose there is a particle with mass m loop. It's in the loop, so I call it m loop. And you are calculating the magnetic moment of a particle with mass ml. Okay? So if you calculate such a diagram, it will look like this. It will be a function of the ml squared over m loop squared. This is because this G minus 2 is just a number. It doesn't have any dimensions. So basically, it's a ratio of two masses, the square of the masses. Now, so that means this mass we know and everything else we know. Okay. So if we know the complete result, we can guess what should be the mass of this particle that's in the loop. At least the mass is known or unknown. Okay. If we can guess the mass of this unknown particle, that's why it's very important. That means we can also guess the mass of the unknown particles. Okay. Now, why did I say that I'm going to do the G minus 2 of the muon, or the magnetic moment of the muon? Why not electron, for example? What's wrong with electron? Well, the electron is really, really light. So, I told you that the term that comes from the loop looks like this. The mass square of that particle divided by whatever in the loop. If we consider electron here, it's basically me squared. Okay? And the next particle possible is muon. I'm not going to any heavier. Just consider muon. Even in that way, if you consider this ratio is 43,000. Okay? So if you invert that, it's a tiny number. And if you really calculate the whole term, it's like 10 to the power minus 10. Insignificant, really. So it's insensitive to any heavy particle. So unknown particle basically means really heavier than anything we know. That means it's practically zero. Cannot be measured in experiment through electron. Okay, that's why electron is out of the picture. Although we know the result of the